Hi everyone. As we get into more of telescopes and their work with light, I have to point out to you one of the most beautiful balancing systems that telescopes take advantage of. There is an electromagnetic spectrum that comes from the sun that goes all the way from gamma rays, very high energy waves, all the way out to radio waves. And most of the electromagnetic energy that comes from the sun is blocked by the Earth's atmosphere. And that keeps us alive because we couldn't have more energy coming in from the sun, so that the atmosphere blocks the harmful gamma rays and the harmful X-rays, which would just cause DNA damage to our cells, and the harmful UV rays are stopped by our stratosphere and ozone, which we'll get into that sometime soon. So our atmosphere blocks all of these 100% of these rays, and the atmosphere absorbs all of these all of these high energy waves. There is a window where the atmosphere does not block electromagnetic waves, and beautifully that window is in the visible light spectrum. And this sun happens to emit much of its energy in the visible light spectrum, and the Earth's atmosphere happens to allow that energy to reach the Earth's surface. And on top of that, our eyes have evolved to act as spectroscopy devices where we can pick up the different wavelengths of the visible light spectrum as colors. So it's a beautiful thing, beautiful balance. And as a result of that, our optical telescopes on Earth register the colors out in the atmosphere. We'll explore that more. There are other areas beyond visible light into near infrared light where the Earth's atmosphere covers many and absorbs many of the infrared rays. That keeps our Earth much cooler, and it permits life on Earth for that infrared waves. There is a nice window right in here where the Earth actually emits out its extra energy and heat. So if you take my meteorology class, you will pay a lot of attention to this atmospheric window where the Earth emits out its extra energy. And then you see in here, which is the far infrared, where much of it is blocked. Then we move into the radio wave window, where we have a very broad window where the atmosphere does not absorb radio waves. And in doing that, we've allowed in the 20th century for the development of radio astronomy using radio telescopes that can perceive the radio waves coming in from the universe. Longer than that, most of the longer wave radio lengths are blocked. Now, we are going to look into optical telescopes and radio telescopes from the Earth, and we are also going to talk about telescopes in space or airborne to pick up gamma rays, X-rays, and ultraviolet rays above our atmosphere. And we are going to talk about infrared telescopes as well that operate above our atmosphere and can detect infrared waves. If you think about this, it's pretty interesting to think about it because these telescopes will be looking at newer galaxies with hotter temperatures, And these telescopes, especially in the infrared range, will be looking at older galaxies with cooler temperatures, not as much energy there. Let's go into it a bit more. This gives you a pretty good, another view of it. So we've got, as I mentioned in here, the stratosphere absorbs most of the ultraviolet light that comes in, saving our skin from a lot more skin cancer than we currently note. So that is the stratosphere that uses ozone to absorb ultraviolet rays. Some of them do get in. UVA and UVB do get in at near the visible light spectrum. And some infrared does get down to that infrared rays do heat the earth, but much of them, many of them, or most of the wavelengths are absorbed in here by the atmosphere as well. You see this broad area here where the atmosphere is not absorbing radio waves. So I thought I'd give you another perspective, another visual to look into for that. When we talk about telescopes, basically we are talking about optical telescopes and radio telescopes on Earth that are acting as essentially light buckets. And when we talk about light, we talk about the electromagnetic spectrum, so that we can have optical telescopes that are acting as light buckets for visible light. We can have radio telescopes that are acting as light buckets for radio waves. We can have other telescopes that act as light buckets for gamma rays, and all the way, like we said here, to radio waves. So that's what telescopes are supposed to be, buckets for light. Basically, there are two types of telescopes, and all telescopes, from gamma rays to radio waves, are basically on these two major designs. There are variations, but they follow the two major designs. The refracting telescopes were the first telescopes designed by the Dutch back in the 1600s. And the refracting telescope is what Galileo used to see Jupiter and basically revolutionize astronomy with his observations. The refracting telescopes use two lenses, one lens to act as the light bucket and another lens to act as the eyepiece. The reflecting telescopes designed later use instead a mirror to gather and act as the light bucket and an eyepiece. And let's go into that a bit more so I can show you a bit. So when we talk about the refracting telescopes that were used very early, they used a primary lens as a light bucket to bring in the light and focus it to a focal point. We'll get into that in a second. And they used an eyepiece. Now, I'm trying to put together a lab that we can replicate Galileo's telescope, which is highly effective, but you'll understand soon why it was redesigned to be a reflecting telescope. And the reflecting telescope looks more complicated, but it actually is simpler. The reflecting telescope takes in all the light all the way down to a mirror that sits at the bottom of the telescope. The mirror is curved, and the mirror angles the light back to a point that is the focal length here. So each of these has a focal length where it angles the light to a particular point. The mirror angles the light in the reflecting telescopes. We'll get into what those arrows are beyond that in just a moment. Some of the disadvantages of the refracting telescopes that Galileo used are the fact that, and Galileo didn't even know this until Newton pointed it out, that there is light refraction. And you've looked into that a bit here. When we talked about a prism, we talked about separating out the wavelengths. And that really helped Newton to understand optics and to understand that telescopes needed to be redesigned. This same principle of looking through a prism and separating out the wavelengths actually moves the images a bit with these colors moving at different angles. So that refraction caused what's called chromatic aberration, and it really took the specificity of the image and distorted it. And when you are looking for something beyond about 20 times its size, that becomes quite an issue. So chromatic aberration was one of the first things that Newton noted back in the 1600s that required a redesign. And I'm sorry, Newton would notice that around 1740 or so. Okay, so I had that wrong. In addition, the weight of this lens that can only be supported by the edges was just too much of a problem. And it's going to be a problem in designing our telescopes as well. Hopefully we'll use mailing tubes and we'll figure out a way to post this lens, but I have to work on that a bit. So the weight of that lens was always a problem. And the lenses are expensive. They have to be ground down very precisely without flaws. You have two lenses, one at the primary lens and one at the eyepiece, which have to be optically designed and optically pure. Tough to do. So refracting telescopes needed to be redesigned. They were redesigned as reflecting telescopes. And what I would say to you is that the focal length in the reflecting telescopes is the distance from the mirror, the light bucket, to the point where the curve on the mirror reflected back to a primary focus right here. Now, in some telescope, that is the focal length. That's what I wanted to point out to you. That is the focal length. And in some telescopes, especially early telescopes, they put their mirrors to view and their instruments to view right here. That wasn't really a way to go. In fact, Newton very early redesigned that to put in a secondary mirror. He put in a secondary mirror that took that primary focus and moved the image out to an eyepiece that was right here. So there is still a mirror, there is still an eyepiece, and there's a secondary mirror that moves the image to the eyepiece in the Newtonian focus. Very, very well designed, and it was looked at later and really improved later to the Cassegrain technique. And the Cassegrain technique is by a French optician who made it a little bit more complex, but as you see, it's a design that uses straighter angles, and this design is used in the Hubble telescope and is used in most of the best optical telescopes around the world. Let me explain to you a little bit. There is still the mirror right here, and there is still the prime focus up here, and the mirror, the secondary mirror, goes right down and focuses to an eyepiece that's right here. There is another type, the Nasmyth, that kind of takes the Newton and moves it out with a third lens. That is used up in Mauna Kea in Hawaii, but it is not as well loved as the Cassegrain. We'll get back to it in a minute.